Hello everyone, I'm Woosuk. I'm a PhD student at UC Berkeley and co-creator of the vLLM project. Today, I'm very honored to be here and talk about the project on behalf of the vLLM team. Okay, let's get started. As many of you may know, vLLM is a project to build the fastest and easiest to use open source LLM inference engine. Our history dates back to summer 2022. Back then, the OPT model came out from Meta, and our lab tried to host the model for a demo for another project. However, we found that our inference service, to be slow and surprisingly expensive. So later on, we started a small side project to investigate and optimize its performance. And this eventually evolved into the vLLM project. Fortunately, we started before ChatGPT and Llama came out, so we were able to release our project at a very good timing when people started to deploy LLMs. Back then, all open source LLM inference solutions were either slow or difficult to use, and vLLM innovated this with great performance and nice APIs. Fortunately, we got a lot of traction from the beginning and has continued to grow very rapidly with the help of community. Now, vLLM is the most popular open source LLM inference solution in terms of number of stars, number of users, and contributors. Yeah, and vLLM is widely adopted across academia and industry. For example, vLLM is used by the LLM event harness library to run the accuracy evaluation benchmarks with high performance. And it's also used by a lot of startups and big companies, including Rika and Cohere presented today. Yeah, and also importantly, you can find a lot of vLLM-based products on major cloud providers like SageMaker, Azure AI Studio, and Vertex Model Garden. Okay, so yeah, why people choose vLLM? Today, I'd like to highlight the 6 particular aspects of vLLM I think interesting and important, and also along with some technical challenges we solve. Okay, first is the broad model support. vLLM supports a variety of models, a wide range of models, including transformer-based text models like Llama, multimodal models like Lava, space-based models, embedding models, and even reward models for training. And this is because vLLM provides a very easy way to integrate new models. First of all, vLLM is based on PyTorch and Hugging Face transformers, which are basically the standard in open source AI. And on top of that, vLLM kind of requires minimal changes to the model code. So the example code on the left-hand side is basically the simplest model inference code in the Hugging Face format. And starting from here, what you just have to do is to replace some specific classes and functions to vLLM APIs, and that's pretty much it. Without complicated conversion processes, vLLM enable all the features, including quantization, distributed inference, and so on. And furthermore, vLLM supports has a first-class support for multimodal models. Actually, the multimodal models are a bit more complicated than text models because different models have different ways to pre-process the input images and input videos. And also, they have pretty diverse model architectures. So to handle this complexity, vLLM provides a very structured API, structured way to register and specify how the input images, videos, and audios are pre-processed and how they are eventually mapped to the tokens in the LLMs. But thanks to this, vLLM now supports almost all popular open large language models and visual language models. And importantly, most of these are actually contributed by the model creators. vLLM is one of the official launch partners of Llama. And we are also partnering with other leading model creators like Mistral and Kwon so that they contribute their model code to vLLM as they want. Yeah, the next is the rich set of features. Okay, vLLM definitely supports quantization. Quantization is very important for us. And the thing is, vLLM supports a wide range of a variety of quantization methods, including FP8, GPTQ, AWQ, and many more. And in addition to that, we also provide efficient gem kernels for this quantization method so that you can get the actual desired speedups from the quantization. Not only the can benefit from the storage, but also in terms of the performance. Yeah, even more, like we also provide the LLM compressor quantization toolkit, which you can use to quantize your own model weights with your own data sets. This is not the only way to use quantization in vLLM. You can use other quantization toolkits like AMD Quark, but this is we provide a very easy way to get started. And vLLM also supports speculative decoding, which is an idea of using a small model to generate a proposal with multiple tokens and let the large original model to verify it. This accelerates the inference process because verifying the multiple tokens at once is actually much faster than generating these tokens one by one auto-regressively. vLLM further extends it with dynamic speculative decoding. So basically, the problem in speculative decoding is that it sometimes wastes compute when the draft model fails to generate a proposed good draft. And this is justifiable when your system has a low rate, when your system load is low, basically because otherwise you will underutilize your GPUs anyway. But this can be a huge performance loss when your system load is high. To mitigate this, we introduced dynamic speculative decoding, which kind of adjusts the proposed length, the number of tokens generated by the draft model dynamically using the system load and also speculation accuracy. This way, we make the speculative decoding always beneficial in terms of the performance. And another important feature in vLLM is automatic prefix caching, which is similar to the radix attention in SGLang and also the prompt caching API in Gemini, Anthropic, and OpenAI. One key difference from the prompt caching API is that in vLLM, the prefix caching happens automatically, pretty much just like a CPU cache. So one good use case is that when basically you have a shared system prompt that tells the model about the task. In this case, vLLM will compute this shared system prompt only once, and will keep it in the GPU memory, keep the KV cache of it on the GPU memory, so that it will never recompute this for every request. Yeah, another example is multi-round conversation, where basically the content of the previous round becomes exactly the prefix of the next round. In this case, prefix caching can help reduce the first token latency a lot. Yeah, another feature is multi-LoRa serving. Basically, when you have multiple LoRa adapters for the same model, vLLM can efficiently handle them with our own group gem Triton kernels using some batching logics. And vLLM also supports structured outputs and tool use. So basically, we kind of integrated with outlines and other third-party libraries to support efficient support for JSON outputs and also tune calling APIs recently added in OpenAI API. And yeah, finally, vLLM is also is kind of like production-ready engine in the sense that it provides a lot of promiscuous metrics about the system status. So you can actually use this for monitor your instances, or and even use them for auto scaling using the Kubernetes or Reserve. Okay, the next is the distributed inference. Nowadays, distributed inference is kind of a must for many of the popular models. However, cross-GPU or cross-node communications are still fragile and error-prone. Actually, this is not super difficult when you make a demo or when you make when you just do some performance benchmark. But in reality, to handle these libraries reliably is actually not trivial. And yeah, like vLLM is here to take care of it for you. Like basically, vLLM handles all the intricacies of like dealing with Nickel and Rico libraries by setting the best versions and also setting the proper flags. And yeah, in addition to that, we also optimized tensor parallelism with our with custom Olitus kernels. Yeah, basically, yeah, Nickel uses a ring algorithm for Olitus, where it splits the tensors into smaller pieces and communicate them into multiple steps. However, while this works very well for large tensors, this becomes extremely inefficient for small tensors. For small tensors, like all-to-all style one-shot Olitus performs much better. So here, basically, each GPU directly goes to all the other GPUs and patches the tensor from them. And this way, we can this kind of like introduces a lot of like redundant communication, but better utilizes the available communication bandwidth when the tensors are small. And this way, we can like finish all of this operation in single step. And yeah, this is a huge improvement for the tensor parallelism case. And yeah, vLLM also supports pipeline parallelism. vLLM is one of the very few frameworks, and actually the only framework that I know of that support pipeline parallelism for LLM inference. Pipeline parallelism is a technique to split the input queries into multiple streams and process them in a pipeline fashion. And this is efficient because like between pipeline stages, you don't have to do expensive collective communications across all the GPUs in your cluster. And there are two interesting use cases. The first case is when you have a very large model, like Llama 4 by B, that you might want to use like your GPU cluster across multiple nodes. In this case, the communication between the different nodes often becomes a bottleneck, and pipeline parallelism can be a very efficient solution to that. Another more interesting use case is when you when you charge your model over PCI connected GPUs. Here, the communication becomes a bottleneck again, and yeah, like in our benchmark, pipeline parallelism is often more efficient than tensor parallelism in this case. Okay, the next is performance, which is the focus of vLLM. Yeah, obviously we use a lot of like optimized GPU kernels inside vLLM. Yeah, like for attention, we use state-of-the-art, fast, open source kernel libraries like XFormers and FlashInfer. While for other operators, we kind of like hand-wrote many kernels inside vLLM. So for example, we have an efficient Triton kernel for group gem, like for MOE. And we also have a efficient kernel for quantized gems, for example, Molly. And then, yeah, like going forward, we are also trying to integrate with torch.compile, which is a core feature of PyTorch 2. The idea here is to like let the compiler automatically optimize the model and generate the efficient kernels for us instead of like us like writing the kernels manually. And with the active collaboration with the PyTorch team, we recently added like experimental support for torch.compile. And going forward, we are really pushing it forward to make sure vLLM evolves together with PyTorch. Yeah, and the performance optimization is not only about GPUs. Actually, with these nice optimizations on the GPU side, we found an emerging trend that CPUs, not GPUs, become the primary performance bottleneck sometimes. And this is fundamentally because of the increasing performance gap between GPUs and CPUs. Like while GPUs are getting faster and faster in terms of hardware and software, CPUs, like evolve much slowly. So to ensure that CPU does not become a bottleneck, we are paying attention to everything happening on CPU in LLM inference. Yeah, one concrete example is, say, when running Llama 3 8B, like with FP8 precision on a single MI300X GPU. So at small batch sizes, like each model step actually only takes a few milliseconds, less than 5 milliseconds. So which means like the extra 1 or 2 millisecond overhead from whatever region from CPU can actually significantly decrease the overhead, significantly degrade the performance. On the other hand, at large batch sizes, say when we're doing the offline batch inference, we can batch thousands of requests together to fully utilize the HPM. And in this case, CPU needs to pre and post process these thousands of requests every step, which can be a huge performance bottleneck if not optimized properly. Okay, for low latency, we use CUDA or heap graph. Basically, if you run your model with a small batch size on eager mode PyTorch, then you will see that like the GPU is idle because CPUs do not launch the kernels fast enough. And yeah, CUDA or heap graph is basically optimize this overhead by bypassing all the Python and PyTorch overheads and provides a very efficient runtime to launch the kernels. For high throughput case, we recently integrated a new optimization called multi-step scheduling. So vLLM used to do scheduling every step, paying the overheads of scheduling, input preparation, and output processing, and so on and so forth. And with these optimizations, vLLM now schedules multiple steps ahead, and thereby amortizing all of this cost, and thereby increasing the throughput. Oh yeah, and also the next is the very important part, which is like open source community. So vLLM is a project owned and driven by the community. Actually, all of the optimizations and features discussed early on in this talk, most of them are actually implemented by the community, not only by the small team at Berkeley. And we really focus on maintaining and growing this healthy and vibrant community, like by joining the Linux Foundation and also by hosting the regular events like meetups and office hours to meet our users and collaborators face to face. And even more amazing thing is that the community is really growing. So like early last year, like the students at Berkeley basically wrote the 100% of the commits, but now we only wrote, say, like 20% of the commits. The other like 80% of the commits were coming from the community, which include the major contributors like Neuromagic, Anyscale, IBM, and Roblox, and also AMD, but also includes all like different companies, all different people from all the different backgrounds who are actually using vLLM in their production. Okay, last but not least, one important major stream of our work is supporting diverse accelerators. vLLM currently supports 7 different hardware backends, spanning GPU, CPU, and even custom AI chips. And importantly, we support all these hardware backends with the same user APIs, the same like OpenAI compatible APIs, or same offline batch inference APIs, so that the user can use them without the deep knowledge of the hardware. And this is possible because PyTorch supports all these models actually. Instead of relying on the external like compilers or formatters like Onyx, vLLM directly uses PyTorch as a middle ground, a narrow way to connect these hardware backends with the hardware agnostic models and utilities. Yeah, particularly for AMD, we started the collaboration since the last Advancing AI event, where the MI300X were announced with the initial vLLM integration. Okay, since then, we've been collaborating very actively, and yeah, as a matter of fact, vLLM was the AMD's choice for the latest MLPerf inference submission. Yeah, and also we very recently, last week, we had a meetup to meet the the engineers and like relevant peoples from China and Texas, basically bring all of them people in San Francisco and meet like face to face. Yeah, and for a small technical meet, basically the process of integrating AMD GPU was also pretty amazing experience for us because of the AMD's mature ecosystem. Actually, like with PyTorch and like Triton integration, and also like and also with a lot of other libraries, like AMD provided a very good like a very mature ecosystem that we basically we didn't have to like reinvent everything for AMD. We basically kind of reuse our existing stack, our existing components with just small like optimizations on the kernel side for specifically for AMDs. So in current vLLM, most of the components, especially the Python parts, the high level parts like scheduler, of course like memory manager, like workers, and even the models, and even like Triton kernels are all shared between NVIDIA and AMD GPUs, so that like when we develop a new feature, AMD GPU backend can also leverage it almost immediately. Yeah, like so. Yeah, these are kind of the list of features that are enabled on AMD GPUs. You can find that most of the features, and actually almost all of the features we discussed early on in this talk, are actually supported by the AMD GPU as well. And we are also working actively to enable all the other features and models that are not supported on AMD GPU today. Okay, in summary, vLLM is a popular LLM inference engine with broad model support and rich features. vLLM ensures high performance by different layers of optimizations, from kernels to engineering on the CPU side. And finally, vLLM supports AMD GPUs through official collaboration with AMD developers. Yeah, this is for me. Yeah, thanks for listening.